So what is specific heat? So specific heat is the amount of heat required per unit mass by a substance to raise its temperature by 1 degree Celsius. And this should be done at a constant volume or a constant pressure. Now, there are basically three models of the specific heat. The first model was given by Dulong and Petit, and it says that the specific heat of a substance is independent of temperature and it is constant for a given substance. And that is basically equal to 3R, where R is the gas constant. Then came Einstein and he said, no, the specific heat of a substance does depend upon temperature. And he deduced some relations. And according to his relation, the specific heat at higher temperatures was found to be matching with experimental values, but at low temperatures his findings were basically of an exponentially varying specific heat, and those were not exactly matching with the experimental findings. Now then came Debye, and he basically improved upon the shortcomings of the this shortcomings of this Einstein model, and deduced a new relation for specific heat and at low temperature, that is basically known as the T cube of specific heats. So what were the shortcomings in Einstein model, and how basically Debye overcame those shortcomings? So the first shortcoming model was that Einstein assumed that atoms in the solid vibrate, all the atoms in a solid vibrate at the same frequency. And now the second assumption was that these vibrations of atoms are independent of each other. That is, one atom vibrating in the solid does not affect the vibrations of other atoms. But Debye said that no, if we have a solid and if there are atoms in it, so if one atom is vibrating, it is also being affected by the vibrations of other atoms as well. And the vibration frequencies of these atoms are in a range from 0 to cutoff frequency, which was called by Debye the Debye frequency, which is nu d, and that is basically the upper cutoff frequency for all the atoms. Now, these are some of the shortcomings of the Einstein model, which Debye worked upon and deduced a relation. Now, I'll show you the relation deduced by Debye. So let me share the screen. Yeah. So you see, Debye deduced this energy relation according to his assumptions, which are basically an improvement of the assumptions made by Einstein. So Einstein assumed, Debye assumed that atoms vibrate in a range of frequency from 0 to nu d, 0 to nu d, and this nu d is basically known as the Debye frequency. Now he basically deduced a relation for energy, and here you see X is basically h nu by kBT, and theta d is called the Debye temperature. Now at low temperatures and high temperatures, we'll try deducing the relation for specific heat and see if the result matches with the experimental findings. So you see, at high temperatures, when T is very much greater than then this X is going to be very small, and if X is going to be very small, then expansion of exponential X, which is basically 1 plus X by 1 factorial, X square by 2 factorial, is nothing but 1 plus X, where higher order terms are basically ignored because these terms are too small. Then we evaluate this integral with this higher temperature assumption, and the value of the integral comes out to be this, and the energy is basically now this thing, this relation, that is 3 n kBT or 3 RT per mole. So specific heat now is basically 3R, which is basically matching with the Dulong Petit law and also matching with the experimental findings, and this is constant. Now at lower temperatures, when T is much greater than the Debye temperature, so here Debye temperature is the upper limit. Since T is much smaller than the Debye temperature, this theta D, that is Debye temperature by the temperature of the medium, would basically go to infinity. Now, since this thing is going to infinity, this integral transforms to a standard integral where the limits are from 0 to infinity and is pi to the power 4 by 15. And the energy value then comes out to be 9n kb pi to the power 4 by 15 and t to the power 4 by theta d, where dq, where this is the Debye temperature, and the specific heat is nothing but 12n kb pi to the power 4 by 5 and t cube by theta d, theta d cube. Now you see all these quantities are basically constant, and even Debye temperature is constant for a particular solid. Specific heat is basically directly proportional to T cube. So this is the reason why we also call this Debye law as the T cube law. Now I have shown here some plots for the specific heat. Now you see this line. This line shows the Dulong-Petit law. Specific heat is 3R, that is constant. Now this is the Einstein curve, and I am curve for specific heat, and as I have already mentioned, that this is at low temperatures is like an exponentially varying function, and at higher temperatures, Einstein law matches with the Dulong-Petit law and also with the experimental results. Now this is the Debye. This solid line is the Debye. Is the findings of the Debye. So you see the Debye curve is basically matching with the experimental values. Here circles are basically the experimental values of the specific heat. So you see and this is basically varying as a T cube or the temperature cube. So you see the Debye model is very close to the actual experimental findings at the lower temperature at the lower temperatures also, but there are some shortcomings in the Debye model also, and I'll be talking about them now. So the first shortcoming is that the Debye model basically totally ignores the contribution of specific heat by electrons. That is, so suppose if I'm giving some energy to a solid, then according to the Debye model, all the energy is used up in lattice vibrations. But in reality, what happens that when I give some energy to the solid, some of it is used in lattice vibrations, and some of this energy is used by electrons to go from ground state to some excited state. So in this way, we are basically neglecting the contribution of specific heat by electrons. Now there is one more shortcoming in the Debye model, and that is the Debye model is basically applicable for only those solids which are having only one type of atom. For example, only carbon atoms are there, and it is not applicable to NaCl because it has two types of atoms, this sodium atom and the chlorine atom. So the Debye model is not applicable for these type of solids. Now this Debye temperature in this Debye model, that is theta d, that is h nu d by t, is also assumed to be independent of temperature. But in reality, what happens that even the Debye temperature is dependent on temperature, and here Debye model fails in that respect. Now in Debye model, it is assumed that only atoms only vibrate with lower frequency. That is only those frequencies which are basically lower than the Debye frequency nu d. But in reality, it so happens that some atom may even vibrate with frequencies which are higher than the Debye cutoff frequency, that is nu d. So you see, these are some of the shortcomings of the Debye model. I have discussed about the Debye model and how the specific heat varies with the temperature, and at low temperatures this Debye model transforms to the T cube law. I hope this video was like very helpful. Thank you so much for listening.